All right, let's talk about one of the biggest ideas in tech right now, neural networks. But instead of just giving you a dry definition, we're going to actually build up an intuition for what one is. And we'll start with a little puzzle. Okay, so take a look at this image right here. It's pretty messy, right? It's a low-res, kind of sloppy handwritten 3. And yet, your brain knew what it was pretty much instantly. You didn't have to trace the lines or anything. It just popped into your head. That's a 3.
And that right there, that's the whole puzzle we're starting with. The thing that is just completely effortless for us is a total nightmare for a normal computer program. I mean, how would you even begin to write code for that? To describe every possible way someone could scribble a 3. This exact problem is why we needed a whole new way of thinking. And that new way of thinking? Well, that's the neural network. As you can probably guess from the name, it's a machine that's inspired by the way our brains are structured. So let's crack it open and see how this thing is actually designed to tackle a problem like this. So, our network, it's got 3 main parts. First, there's the input layer. Our image is 28 by 28 pixels, which is 784 pixels total. So we have 784 neurons, one for each pixel. Simple enough. Then, at the very end, we have an output layer with 10 neurons, one for each digit from 0 to 9. And in the middle, well, that's where the magic happens. We've got these mysterious hidden layers.
Now, when you hear the word neuron, your mind probably jumps to biology, right? Brain cells and all that. For our purposes, just forget all that. In a neural network, a neuron is way simpler. It's just a little container that holds a number, specifically a number between 0 and 1. We call this its activation. You can think of it like a dimmer switch for a light bulb. 1 is fully on, 0 is completely off. That's it.
Okay, so that brings us back to those hidden layers. What are they even for? I mean, what's the big idea here? What's our best case scenario for what they're actually doing to get us from a bunch of pixels to a clear answer? You know, let's use a different number to think about this. A 9. When you look at a handwritten 9, you're not really seeing a grid of individual pixels, are you? Your brain is doing something much smarter. You see components, parts. A 9 is basically just a circle on top of a stick, right? An upper loop and a vertical stem. So, in a perfect world, our neural network would figure this out too. Maybe some neurons in one of the hidden layers would become little loop detectors.
But wait, we can go even deeper. Think about it. How do you even recognize that loop? Well, your brain recognizes that it's made of even smaller pieces, a bunch of short, curved edges all pieced together in the right way.
And that right there is the whole genius of a layered network. The idea is that the first hidden layer learns to spot the simplest things, like tiny little edges from the raw pixels. Then, the next layer takes those edges as input and learns to combine them into bigger patterns, like loops or straight lines. And finally, the output layer can look at those patterns and say, aha, a loop and a line, that's a 9. It's this beautiful hierarchy of recognition. Okay, so we know what we want the layers to do. But how does one single neuron, how does it actually think? How does it decide, yep, this is the pattern I'm looking for, and light up? Let's zoom right in and see how the sausage is made.
All right, so the first truck up a neuron sleeve is something called weights. Every single connection from a neuron and the layer before it has a weight attached. You can think of these like votes. Let's say a neuron wants to find a specific curved edge. It will assign a positive weight, let's make it green, to all the pixels that make up that edge. It'll also assign negative weights, we'll make those red, to the pixels around it to vote against them.
The second tool is called the bias. After the neuron adds up all the votes from the weights, it adds this one extra number. The bias is basically a thumb on the scale. It's the neuron's way of saying, okay, I don't want to get excited and light up unless the total vote count is at least this high. It sets the activation threshold.
So let's put it all together. The process inside every single neuron is actually pretty simple. Step 1, it calculates the weighted sum of all its inputs. Step 2, it adds its own special bias. And step 3, it runs that result through one final squishification function. Okay, that last step, the squishification function, I love that term. Technically, it's called a sigmoid function, but squishification is just better. Its entire job is to take whatever number pops out of that calculation, it could be a big positive number, a big negative number, whatever, and just neatly squish it down so that it fits in that 0 to 1 range that we need for our activation.
All right, we've looked at the tiny little Lego bricks, the layers, the neurons, the weights, the biases. Now it's time to zoom all the way out and see the giant castle we've actually built.
Get ready for this. For this, frankly, pretty simple network that just recognizes handwritten numbers, there are almost 13,000 individual weights and biases. 13,000! That's how many little knobs and dials we have to tune to get this thing to work.
And if you really zoom out, that's all a neural network is. Seriously, this whole massive, complicated-looking system is just one giant mathematical function. A ridiculously complex one, sure, but it takes in 784 numbers, our pixels, and it spits out 10 numbers at the other end. That's it.
I love how the source for this whole explainer, 3Blue1Brown, puts it. He says it's an absurdly complicated function, but it's just a function nonetheless. It feels like magic, but nope. Under the hood, it's just a whole lot of math.
So, what does it mean when we say a network is learning? Well, what we're really talking about is just the process of getting a computer to find the right setting for all 13,000 of those knobs and dials, the combination that actually solves our problem.
Which, of course, leaves us with the million-dollar question. Or, I guess, the 13,000 knob question? If you have that many dials to turn, how on earth does a computer figure out the right combination? That process. That's the real secret sauce, and it's exactly what we're going to dive into next time.